Hey, welcome back. In this lecture, we're going to be talking about the basic implementation of the disjoint set structure. Actually, what we'll be doing is looking at a few implementations and sort of figuring out why the one that we tend to use is better. And then the lecture after this will be going over some optimizations of that idea. So we talked last time about the disjoint set ADT. We're basically saying, actually, let me just put a title on here first. So here we have the disjoint set ADT. And it basically consists of two core operations, union, where we have here set A and set B. However, they happen to be notated, and also returning some name of some set, and then we say find, and then some element E. Now, in practice, the particular parameters we'll pass in will be slightly different because it'll depend how we're notating our sets, how we're notating our elements, and so on. But conceptually, this is what we're trying to do. We want to be able to union two sets, and we want to say, given an element E, return the set that it's in. And those are the core operations we're dealing with. We also, of course, have constructors and adding a new element to the universe and things like that. But these are the two core ideas. So when it comes time to deal with an implementation, well, there's a number of places we might start fiddling with these kind of ideas. One thing we can do is pick one operation to try and optimize, and then say, okay, given that we've got this operation working, now how would we make the other one work? And so that's one way to start, is to try, we don't have to start that way, but that's one way to do things, is to try and optimize one operation. And then once we've optimized that one operation, consider implementation for the other operation. That's one way to go about doing this. Or even in general, when you're faced with a new ADT, you might pick an implementation that makes a couple of operations work very fast, and then see, okay, now how would that affect how we code implementations for the other ones. So we'll start by optimizing find. We're going to say, given an element, we want to be able to return the name of the set that that element is in as quickly as possible. And then we'll see how union sort of falls into that. Now, there's a few different issues we might deal with here. Firstly, we have the question of, what info is available for the elements? Because, if we have a hash function available, for example, we could use hashing. If we have the less than operator available, we can use, if we have a hash function, we can use a hash table. If we have the less than available, we could use, among other things, a search tree, perhaps a skip list as well. So we ask what info is available, and depending on the info that's available, we might have different possibilities for looking up a value. And what we'd like to do is focus on the core idea of the disjoint set operation first, or at least a core idea of what if we had the absolute ideal element set, then how would this affect the disjoint set implementation? So just to sort of consider that and get around the idea of looking up a particular key, which we've already seen a number of ways to do, what we're going to do is assume, just for the moment, for the sake of the early discussions of all this, assume keys are the integers from 1 to n, whatever n happens to be. And so certainly if they weren't, then you'd be worrying about some other factors. Well, okay, if they're not the integers from 1 to n, then we maybe have a search tree involved or a hash table or whatever else we might do. And of course, you may have no information whatsoever, in which case you're sort of now trying to deal with other things. But let's assume for the moment we have those kind of keys, just so we can say, okay, if the keys are the most optimal keys we might come up with, and we'll talk about why they might be very nice in a moment, then how does that affect things? Taking away the whole issue of searching on a key to get a particular set name the removing the search concepts or any of the other things we've talked about, stripping that away and having the most optimal key set possible. Now, how is that going to how will that come into play with the implementation? And there you'll see in a moment, or you'll see eventually why we're going to start in this manner. It'll allow us to focus on the core ideas behind the implementation, and then we can say, well, we'll come back and talk then about the more general situation of what happens if we don't have those opportunities or that kind of key set available. So focusing on those the best key set possible will enable us to sort of focus in on the disjoint set part of this more, rather than the looking up a key part of this. And so in that, or actually, I'm going to put this back here. In that case, what you can do is here, you can say the keys are array indices, which is why this is such a nice data collection. And if the keys are the array indices, then one possible implementation, if the keys are array indices, is to say, well, A of key holds your set name, and of course that's constant time to retrieve then. If whatever cell is at that key holds your set name, you can retrieve the set name in constant time, which is as good as we could possibly ever get find. If our keys are from 1 to n, let them be array indices, and say doing a find on a key is equivalent to using that key as an index to an array, and then we can retrieve our set name in constant time. So for example, if we had a situation like this, where I've got now, we'll say 1 and 7 and 4, and these are in set A, and I've got, say, 2 and 3 and 5, and these are in set B, and I've got 6 and 8, and these are in set C, then what I have here is, let's set up an array, 4, 5, 6, 7, and 8. And we say 1 and 4 and 7 are in set A, and 2 and 3 and 5 are in set B, and 6 and 8 are in set C. So that would be then how, if we're going to try and optimize find, how we might deal with implementing this disjoint set structure. Because what we're saying now is, well, that's all it is, an array of characters. And so now if I wanted to determine whether 5 and 8 are related, I say, well, do a find on 5, and that returns B, and do a find on 8, and that returns C, and since B is not equal to C, then therefore 5 and 8 are not related. And I can do that in constant time because each of those find operations would be constant time. So this would be as good as find could ever get. Constant time find operation, and therefore that at least half of this ADT is optimized. The question is now, if we're going to have this set up and to optimize find, what are the consequences to union? If I want to do a union of, let me say, set B and set C, what's involved with that? And what would be involved with that for this picture would be to say, well, if I'm going to merge B and C together, and let's just say we're going to give it the new name D. We'll call that name D. What I'm essentially doing is saying now those two sets are going to be part of one set. So if I was to draw this again, what we're saying now is we had here sets 1, 4, and 7, and here's set A. And now we'll have 2, 3, and 5, and 6 and 8, and these will all be some new set D. That is, what I need to do here, I had here, this was originally A, this was B, 4, 5, 6, 7, and 8. In cell 3 I had B, A, B, C, A, C. What I need to do with this array is basically change this, 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 and this all to D. Because element 2, 3, and 5 used to be in set B, and now they're in set D, and element 6 and 8 used to be in set C, and now they're in D. And the question is, what is this running time in, say, the worst case? And then what would be the average case, or even the best case? What would be the running time for this operation? And I'll pause for a moment while you give that some thought. Okay, in the worst case, well, we see that here. If you started looking down the array, we had to change the very last cell even to D. So we couldn't stop looking early because cell C had to be changed at the very end to a D. And so you think to yourself, okay, what if I only had to change cells 2, 3, 5, and 6? And cell 8, if the number 8 was not in the original set C or set B, we wouldn't have had to change it. And so maybe in the average case, or even the best case, maybe only a few elements near the center need to be changed, or a few elements near the beginning need to have their set name changed, and I wouldn't need to traverse the entire array. And the answer is you'll have to traverse the entire array anyway. It's easy for us to just sort of look at this and say, oh, I can easily see where the B's and C's are. But what we're really doing, though faster than we really realize we're doing it, is quickly reading down the letters and finding out which ones are B's and C's. If I cover this up, you don't know whether you need to search the rest of the array or not. And likewise in the computer, the only way the computer knows that all of the elements have been changed correctly is by looking at all the elements one by one, which is what we really do here ourselves with our own eyes, but we just do it so quickly, we have this feel of, oh, just jump right to the B's and C's and change them. But if I was only going to reveal to you the cells one at a time, I'd say, okay, there's cell 1, there's cell 2, there's cell 3, there's cell 4. You'd be checking these one by one to see which ones need to be changed to D and which ones don't. And the computer will need to do the same thing. We don't have any other structural information here about what elements are in what sets. The only way I know something is in set B or is in set C is because I've read that cell and determined that the character there is a B or a C. So the computer could never be entirely sure the union was done until it looked at every cell. And so even in the best case, your union here is going to be constant time. Your find it'll be linear time. Your find is constant time, but your union is going to be linear time, even in the best case. Because anytime you do a union of two sets, you'll need to traverse down and see for every single element, say, if it's part of one of the two sets that are being merged together, then make it the name of the new set. And so you're able to do that here, but you don't have any special knowledge that cell 8 is or isn't C. You don't know that it is or isn't C or isn't B until you actually read that cell. And so every union will involve traversing down the array and changing every cell we see that is a B or a C to a D. But we don't know where those B's and C's are, so we will need to look at every single cell to be sure we've changed everything that needs to be changed. There's no way around that. There's nothing find can do extra to make union easier. Union, we're stuck with a linear time. Now you might say, well, what if I have other information as well stored in other arrays or whatever? And yeah, that's certainly possible. What we will start doing then is getting to the point where we don't need this structure. Because if we're going to maintain this structure, we're going to need to change those cells. And what we will find then is if we try and store additional information to make finding those cells easier, the storage of that information will be such that this array will be kind of useless to us. And that's what we're going to start seeing. But anyway, this is one way of implementing things. Simply do a find on the, given an array index, you look in that array cell, and there's the set name. And then you're done. So one thing we might have done here is to point out, well, now let's go back the other way and say, well, okay, with this situation, find's really fast, but because I need to change all the individual cells that need to be changed, and because I have no idea which cells those are, I have to search the entire array every time. There's no way to improve union. What if I had started the other way around and said, let's optimize union first, and then try to figure out find from that? What would be the consequences? And the answer there is, well, how might we optimize union? And the one thing we might do is say, well, let's take these same sets and have here, let's build linked lists out of them. Here's set A. And here's set B. And here's set C. So those are our three sets. Now, when dealing with, of course, we probably have sort of, we could perhaps have a list object with a head pointer around here. We need some pointer to the fronts of these lists, but we'll deal with that in a moment. Let's just say we have these lists and we have access to the front nodes. Now, the reason this is a nice representation for union is because since the sets are disjoint, I only need to have somehow indicate that some elements are part of another element set. There's no, if you're going to take any two random lists and union them, you need to try and eliminate duplicates. But we know these are disjoint sets, so there's no duplicates to be involved. We don't have to go through and say, well, if I kind of dump all these lists from elements from two lists into one large list, then I've suddenly got to figure out and make sure there's no duplicate of an element somewhere. But we don't need to worry about that here. I could just do something like saying 0.7 to 2 instead of to null, and now all these elements are part of one large list with one pointer assignment. And so as a result of that alteration, union could be made to work in constant time. Before we said find could be constant time. Now if we have this arrangement where instead of saying look up on the key, get the set name, and optimizing that idea, what we're optimizing here is the ability to take two sets that do not share elements and merge them into one set by way of a pointer assignment. By way of saying, well, one set will point to the other one by virtue of the last node in one set pointing to the first node of the next. And now if you were to follow the collection along, they're all part of one list. And we can then say, okay, well, two elements are related if they're part of the same list. But we'll talk more about that in a moment. So this is an implementation, storing things by set, in a linked list representing each set rather than individual keys and looking up on those keys to get the set names. This is a way that will allow us to accomplish a union in constant time. The question is, what can we be done about find? First, what's the running time, but more importantly, how do we even do it to begin with? And at this point, let's say we somehow have one of those lookup structures we talked about. What we'll do is we'll assume for the moment you can get pointer to a node. Because if we're going to build linked lists, then we have these linked list nodes. And let's just say you can assume you can get a pointer to a node. Again, we'll talk about, well, actually, we don't even need to talk about that. That could just be done like this. Given that we still have integers, keys 1 through, make that 1, 2, 3, 4, and so on. Given that we still have keys 1 through n as our key, or integers 1 through n as our keys, I could just simply say, well, here's a pointer to 1, and here's a pointer to 2, and here's a pointer to 3, and we could do something like that. And so I could, instead of saying what we did before, which was given my key, the cell at that key contains my set name, now the cell at that key will point to a linked list node containing my key, and then these linked lists, how these linked lists are arranged will be basically our lookup procedure. So we haven't added any power we didn't have before. The keys are still integers 1 through n, just like in the previous example, except this time, instead of storing the set names, so that I need to traverse the entire array and change the set names, now I simply have the list node, so that I have the ability then to traverse across the entire, or traverse across the list, get a starting point in the list, and traverse to the end. And so that suggests to us that one possible way of dealing with these set names, of dealing with find. No matter where I am in this list, if I'm trying to find cell 1, or I look up cell 4 and get a pointer to there, or I say I want to do a find on 7, and the array gives me a pointer to node 7, and I start there, or I say I want to do a find on 2, and the array cell gives me a pointer to 2, and I start there, or at 3, or at 5. No matter where I am in this list of now 6 elements, If I keep traversing forward, I will end up at the end of the list. 5 in this case. So, what if we come back to our original diagram, and we say this is how we were dealing with things to begin with. We said here, oh, we got 1, 4, and 7, and that was set A. And we have 2, 3, and 5, and that was set B. And we have 6 and 8, and that was set C. When we talk about these set names, we don't particularly care about what the names really are, whether it's A or B or Chicago or Boston or X or whatever we're going to name these sets. It doesn't really matter. The point is that we want to be able to say, if I look up 2 elements, I want their names to be the same. If I look up 2 other elements, I would want their names to be different. What those particular names are isn't really too critical, as long as elements in the same set have the same name. So what if instead of worrying about letters, I name the set for some representative element? Say 7 here, say 5 here, and say 8 here. That is, this is set 7, set 5, and set 8, rather than set A, set B, and set C. And the question is, why is that relevant? And the answer is, well, if we go back to those linked lists, before I did the union, and I had just this collection, I could say, no matter where you start in the collection, you look up the key in this array, and that gives you a pointer to that node. No matter where you are in this collection, I could traverse to the end, which used to be this node. I can traverse to the end of this list, and when the next pointer is null, that means I'm on the last node, read the integer, or whatever, read the key, but we said for the moment our keys will be integers 1 through n. Read the key in that node. Take that as your set name. If I'm looking up 1, I'll eventually land on this cell. If I keep going forward, I return 7. If I'm looking up 4, if I do look up the 4 in the array, get a pointer to 4, and I start traversing forward till the next pointer is null, I end at 7, return 7. If I look up 7, I'm right there already. The next pointer is null, so I know to stop, return 7. All 3 of those values, if I started at that node and went to the very end of the list and returned the key inside the last node, well, that key is 7. Likewise here, all of those, if I traverse to the end of the list, I would get 5. You go from 2 to 3 to 5, or you go from 3 to 5, or you start at 5 and you're already there. But the point is, I guess I didn't draw the null on the diagram. We point as 5's next pointer points to null, and so what we can say as well, since 5's next pointer points to null, 5 will become the name of this set. And then what happens is when we do the union, and we have 7's next point to 2 instead of null, now when I do a lookup on 1, I go from 1 to 4 to 7 to 2 to 3 to 5. Or when I do a lookup on 4, I go from 4 to 7 to 2 to 3 to 5. And from 7, I go 7 to 2 to 3 to 5. So now, not only do these elements all end up at 5, but now that I've pointed the next, from pointing it to null to pointing it to the front of the other list, now all of these end up going from 7 to the start of the other list and proceeding to 5. And now if I do a find on any of those 6 numbers, I'll end up at 5 after that union. So one way to arrange these then. The union is constant time because it's only a pointer assignment, assuming, of course, we have pointers to the relevant sets, which we'll talk about in a moment. And then find is simply a matter of traversing down any linked list until you reach the end. When your next cell is null, then you know you're on the last node of the linked list, and you return that key, and you'd be done. And that could take a while, traversing that entire linked list, if it gets longer and longer and longer. So one thing we might do is approach it in terms of a sort of a situation where, why would I want, after looking at 7, or going from 1 to 4 to 7, or from 4 to 7, to start at 2 and have to search through that entire list? Why couldn't I have instead done things this way, where I have Here's 1 and 4 and 7, and since 7 is null, we take 7, the last node, the one with a null for the next pointer, as the representative element of the set. So if I'm looking up any of those, I start on any of these nodes, traverse to the end of the list, I return 7. And then here we had same thing for 2 and 3 and 5. Or if I start on any of those nodes and traverse to the end of the list, well, I say the last node before my null is 5. And if I want to do a union, why not simply point 7 to 5? Now, if I look up 1, 4, or 7, I still eventually end up in 5. Just like I would have before, but however long this list was behind here, I was able to skip all over it. I went directly from this root, or this node to the last node of the other list directly. Instead of winding my way from 7 to 2 to 3 to 5, just point from 7 to 5 directly. And that will make traversing this path a little faster. And in fact, what we start having now is a tree-like structure. We don't have one continuous list. What I have now is perhaps a number of lists merging into different spots, and it starts to look like a tree. And that's what we're going to be dealing with here. This is going to be known as an up tree, where we have no child pointers. The goal here is to have a parent pointer. So our up tree node looks like this, where we have some key, and maybe we have an information record as well. That's not too important. And then some pointer. So I have a key and an info, and we're not drawing the info, we're just drawing the key at the moment. And then I also have some pointer, and that points upwards to the parent. And so what we'd be dealing with here would be something like this, where I have 1 pointing to 4, pointing to 7, and I have here 2 pointing to 3, pointing to 5, and then 7 points to 5 as well. And this altogether would look like that. Where now I've pretty much got a tree structure. 7 and 3 would be the children of 5, but this tree structure doesn't keep track of children, it keeps track of parents. So 4 is the parent of 1, 3 is the parent of 2, 7 is the parent of 4, and 5 is the parent of both 7 and 3. Now the question is, well, why is this helpful? The answer is, well, what we have here, if you build things out of up trees, what if you had instead a collection like this? Say we have here 1, 7, and 4. 1 points, actually, I'll just leave it like this. And now maybe 4 points to null. And here you could have had a linked list. Maybe we have here 2, 3, and 5. And 5 points to null. And then you have, here 6 and 8. Those are your 3 sets. Notice that I'm going to need to look at 3 pointers to be able to figure out that 2 is not in this tree. I'll have to look at 2, and then from 2 I look at 3, and from 3 I look at 5, and from 5 I reach null, and so I say, well, that means 5 is the last node, and I would return 5. In this tree, even though there's the same number of nodes, I don't need to look at all those nodes. I can go from 7 to 4, or from 1 to 4. So here I say 2's pointer is not null, 3's pointer is not null, 5's pointer is null. Great. Then 5's the last node. But I had to look at 3 pointers to do that. 2's pointer, 3's pointer, and 5's pointer. And here, in this tree, the most pointers I need to look at would be 2. 1's and then 4's, or 7's and then 4's. And in general, you could have either a very long list or a situation where you have a number of places all pointing to the same parent. Just like here, 1 and 7 both point to 4. And this is going to be the better arrangement. Reason being, in the worst case, if you have this long list, find has to search, you want to look at the very last node, you have to search up node by node until you hit the root of this up tree. Where here, if everything happened to point directly to the root, then in one constant operation, you're from your node to the root of the tree. Here you have to search through the entire linked list in general. Here, when everything points to the root, you can jump from any other node to the root right away. And so trees will be more advantageous than lists in this respect. We won't be able to do unions any faster. Ultimately, we have a null list pointer and a null parent pointer on the root, and I either point 4 to 5 or I point 5 to 4. One of those two things happens, depending on how I coded my method. But it's this part that we want. We want the ability to say, let's have as many values as possible point directly to the root, because that will speed things up. And so that's why this application will be appealing. The idea will be that when we're done with this part of it, or when we set up this part of it, what we will be able to do is say, well, first union be constant time, as we already said. Find in the worst case will be order n, because we can have one large set of all the elements arranged in a list. But it will turn out that in the average case, let me write down here, we can get logarithmic time for find. If we have things arranged in a balanced tree format rather than a node format, or I'm sorry, a list format, then we would expect if things are arranged more in a balanced tree fashion, then the tree height would be log n, and that would mean the path from the deepest leaf up to the root, which is what we're essentially searching here, from the deepest leaf up to the root. If that would be our situation there, and that would be logarithmic. So if you have a tree, then in the average case, you expect your tree to be roughly balanced. In the worst case, it wouldn't be, just like a binary search tree. And so those would be the times we get. Now we'll come back to that in a moment, but we've done a lot of talking about theory here. Let's actually look at some code to sort of make this somewhat concrete. What we will do here, let me draw these sets again. At a situation like this, where we have those, and we have here 2 and 3, 5, and we have here 6 and 8. And we're going to be making two assumptions for the course of our discussion. Assumption 1 is that we can enter to our uptree node. And I talked already about why that was possible. We said, well, if it was possible before to say, I can assume all my keys are the data from my keys are the numbers from 1 to n, and I can just look up the key as an array, use the key as an array index into an array, and find the set name. We have said also, instead of using the set name, if we are looking for an uptree node pointer, we could have been dealing with that as well. And so I can say, well, we'll assume for the moment we have the keys 1 through n, and then what we'll then say is, well, check that key and follow that pointer to the node. Now notice, if we were to now store inside every node the set it's in, we'd be back to square one, which is why we didn't do that. The whole point was to say, let me traverse and get a representative element, because now when I have 7 points of that list, or the tree, or however we're going to do things, now I don't need to go back and change 1 and 4. And that's the strength of this implementation. When 7 stops pointing to null and starts pointing to 2 or to 5 or wherever else it points, 1 and 4 naturally have their set name changed. Because it would be bad if I said, well, if you want to merge these two sets, I need to look up 1 and change its set's name, and look up 4 and change its set name, and look up 7 and change its set name. Here now, everything in this list changes set name automatically, which is very nice, because the way it takes a little longer to find the set name. You need to traverse to the list to do it. But I don't have the situation where I need to look down all my values one by one, or look them up one by one and start changing set names like I did before, where I'm storing the set name in every cell. I need to change it in every cell. Here, I simply say, well, I only make one small change. Union's very fast. The consequence is, if I want union to work that way, I can't go saying, well, store the set name in every node, because if I store the set name in every node and I want that set name to be accurate, would need to go and change it in every node, which wouldn't be worth it. So that's why we do it this way. That's the strength of this implementation. As I say, as soon as 7 points to 2, 1 and 4 and 7 have had their name change from set 7 to set 5 with one pointer assignment. The downside to that is it takes a little longer to find what set you're in, but it does mean you can do unions quickly. But that's why we're trying to focus on that idea. So we're saying, don't worry about how we get pointers to these list nodes. Let's just assume we can. And likewise down here, just assume we can get pointers to these tree nodes based on the key. And we looked at the one way to do it, the lookup array. And if we didn't have keys that were 1 to n for the integers 1 through n, we'd have an AVL tree or a hash table for lookup. But we'll assume we can get whatever, if we want the node 6, I can obtain a pointer to it. And if I want the node 7, I can obtain a pointer to that, and whatever. And we'll just assume that's the case, so we can focus on the core disjoint set ideas. Secondly, we will assume you do a union based on the tree roots. For example, union 5 and 4, not union 6 and 7. 5 and 4 are roots, so we can do a union on 5 and 4, not 6 and 7. So if 5 and 4, by virtue of being set roots, are now these set names, that's fine, because we're passing in those names for union. We're not going to be passing in the average name of the average element. We'll simply be passing in the names of the sets. We'll relax that too once we reach the end of all this, but for now, those will be the assumptions we make. In addition to the keys are all the integers 1 through n, we'll say because of that, because the keys are the integers 1 through n, we can go ahead and look up an array and get a pointer to an uptree node. So we can assume that getting a pointer to a node, looking up cell 7 and getting that pointer, looking up cell 6 in the array and getting that pointer, getting a pointer to an uptree node is an easy and very fast proposition. And then second, we'll assume that whatever we pass into our union is always going to be tree roots, not average values elsewhere in the tree. So now, that means let's first look at union, and let's say we have 2 pointers to the roots of the trees, node pointer A and node pointer B. And we say, okay, so here we have that's a pointer to a root of one of these uptrees, 4 and 7, and then here we have B, and so now we're going to try and union A and B. Well, one way we can do that is just to say, well, take the root of one of these and point it to the other one. Now when I do a find on 2, 3, or 5, I'll take that extra node and go to 4, and so now 4 is the name of this set for all of those values. And so I can say here, all I'm really doing is saying that the pointer field of B should be pointing to A. And that's really the only thing involved in union, which is why it's so fast. All we're saying is, well, given that I have a pointer to the root node of the second set, take its PTR, its pointer value, and point it to the root of the first set. Now the two are union. That's all there is to it. And the reason they're now, counts as union is because before I made that merge, if I did a find on 1, I would get 1, then 4, and then null, so I'd return 4. If I did a find on 7, I'd have 7, and then 4, and then null, so I'd return 4. And of course, if I return a find on 4, I return 4. Likewise, if I did a find on 2 or 3 or 5, I would look at 2 and then 3 and then 5. For doing a find on 2, I do 2, 3, 5, null, and so that means 5 is what I return. Now, after this union, after that one line of code, now when I hit a 5, I'll proceed to a 4 and then to null, meaning a find on any of those should now return 4, because that's the lastmost node before the null. So just doing this one union now changes the set name the 3 of those return. It now returns 4 instead of 5 through that one line. So union's very nice in that regard, because just one line solves the union problem. As far as find goes, that's just a traversal up the tree. So if now I've got this setup here where I say, here's no, and here I have 4, and 1, and 7, and 5, and 3, and 2. And let's say, we'll say that node 2 is going to be what we're trying to find. And so we say here, save here find, and we have here a node pointer x. We'll return a node pointer as well. I could have returned the key, so eventually what we want to do is reach the node 4. And at that point I could return the key 4, but again, all we're going to be doing is comparing the results. The result itself is kind of meaningless as long as as long as other elements and other sets don't share the same name. So I could return 4, or I could return, seeing as I'm returning a pointer, I could return the address of the node containing 4. And if I look up some other value and it returns the same address, then I know they're in the same set. If I look up some other value somewhere else and it returns the different address of a different node, then I know it's not the address of this one, and thus they're in different sets. So I don't even need to go so far as to return the key. I could just return the address of the node. So this works out fine. And all we say is, well, let's have some temp pointing to that spot, and then move it up one node by one node until we reach the root. So I can say, well, create a node pointer temp, and I'll have temp point to the same place as x does, and then I can say, as long as parent of temp is not equal to null, what I will do is say that temp points up to parent of temp. So I say, well, is temp ptr equal to null? No, it's not. It's equal to, points to 3. So I move temp to point to there. And I say, is temp ptr pointing to null? No, it's not. It's pointing to 5. So I change that and point this up here. And I say, is temp ptr pointing to null? No, it's not. It's pointing to 4. So I move up to whatever it was pointing to, and now I say, now is temp ptr pointing to null? And yes, it is. So I stop there. But once what I'm pointing to by temp points to null, then that's the parent. And so at this point, I can then just return temp. That's all we're doing. I'm positioning a pointer here, and then I'm saying, as long as my parent pointer is not null, jump to where it points to. Is my parent pointer null? No, jump to where it points to. Is 5's parent pointer null? No, jump to where it points to. Is 4's parent pointer null? Yes. So 4 must be the name of the set, and I can go ahead and return that address, or I could have returned, if I wanted to, temp arrow key, and that would then extract the key from this node 4 and return that. The point being that all that's going on here is I'm using a while loop to take a temporary pointer, traverse it up to the top of the root, and then return that. Just like going from the beginning it's just like going from the beginning to the end of a linked list. Same idea. As long as the next node is not null, then you move to the next node. And that's all there is to it. It'll be dependent on the depth of that wherever we start, clearly. Here, if we start at 2, we have to go through all those nodes to reach the top. And so that's why we said in the worst case, the depth could be linear, and we end up with linear time. In the average case, we expect we'll get somewhat of a balanced tree. And so we then, in the average, we'll have log n time. So that's the idea of the basic implementation. We saw union, which was just one line of code, and now we've seen find, which is just these few sorted lines of code. We don't even technically need the temporary variable. If you were not squeamish about changing x, you can just have x traverse to the top, and all you would need would be these 2 lines and that third one there. But that's union and find, and that's really all there is to say about it at this point. Rather than start the optimizations, I'll just do them in their entirety in the next lecture. But what we've managed to do here now is, as I said before, we've got a constant time union and a find that is, of course, worst case linear, and the average will be logarithmic. And so that's already better than we had with the other implementation. When I was looking up the find key to get the set name, I could get constant time find, but I had to have linear union. I couldn't improve that. Now I get constant time union, but I don't have to have linear find. And in fact, in the average, find won't be linear. It would be logarithmic. And what we'll start doing next time then is to gradually push that find time, even make that even faster and faster. And ultimately then it'll be very quick. So we have room for optimization here that we didn't have before, and that's going to be important. Subject, of course, to the earlier assumptions we wrote up. where we said that we can go from the pointer to the uptree node, and we're not counting that or worrying about it. Just assume you can get a pointer to an uptree node. So we'll talk about all that next time. For now, we're done, and I will see you later.